Christopher KNOROWSKI, CTO of SensiML Corp. And he's going to talk about suitability of TinyML for addressing predictive maintenance in high-tech manufacturing. Thank you.
Okay. Yeah, thanks everyone. It's really great to be back doing these in person. It's one of my favorite events, the TinyML conference. It's been a really good event. Met a lot of great people here. My name is Chris KNOROWSKI, and I'm the CTO at SensiML. And I put together this talk with our partners at Adaptix, and specifically my colleague Steve Hauser, who we both worked really closely on getting this project up and off the ground. And so I kind of want to give you an overview of a case study for one of the projects we did, and the suitability of how we found TinyML fit into the predictive maintenance in high-tech manufacturing. Okay. So before I get into the case study, just a quick introduction for SensiML. So what we do is we create a TinyML toolkit for application developers to rapidly build smart sensor algorithms. And that consists of a data collection and annotation tool, along with the SensiML Analytics Studio for building, using AutoML to build machine learning models that can run at the edge. And then our partners at Adaptix have created the EdgeOps Autonomous Systems platform, which is really excellent at data orchestration and ingestion, knowing when to run the predictive analytics models, as well as being integrated tightly into the manufacturing process so that they're actually part of the machine control workflow. So this case study I'm going to be talking about today was one project we worked on with a leading semiconductor manufacturer in the world, where they were interested in adding predictive maintenance to their photonic optical alignment manufacturing process. And the challenges they were having were a lot of unexpected downtime and also low yield for the network component that they were creating. And they were having difficulties understanding the root causes of the problem. And so for their system, their domain experts they'd gone out and they've gotten a bunch of different parts to create the machine. And so when they put it together, they didn't necessarily have a holistic view of the entire system. And so it was challenging for them to identify where the root causes of failure coming from to improve the yield of their overall process without that high visibility. So what we set out to do was implement kind of like 4 different key aspects to improve that process and improve the yield. So the first was to identify issues with the current process leading to low yield. And one of our first successes with that is when we went in, we outfitted the entire machine with over-the-top sensors to start monitoring the vibration. As the machine went through the different stages, we were collecting the sensor data, annotating that data, and we were actually able to identify different clusters which were kind of anomalous. And it turned out that when we went and worked with the domain experts to understand what was going on, they were overloading, putting too much load on that robot arm. And so they were able to collect that process and lead to the system not wearing out as quickly. The next kind of key aspect is to identify indications of equipment failure to prevent downtime. And the only way that you can really do this is if you're involved in that entire process. So we are attaching over-the-top sensors to the machine, as well as ingesting the sensor data from the machine itself. And by doing that, we were able to build predictive models that were actually able to start predicting the equipment failure. We did that by working very closely with the domain experts to understand which parts of the machines were breaking down, as well as to kind of get an idea of what sensors would be able to detect those sorts of failures that they were seeing. Another key pillar is to improve yield by increasing the throughput. So if you can double the amount of parts you can produce in each of these machines, then you don't even necessarily have to increase yield, but to increase your overall throughput. So one of the really interesting aspects of this entire process is because with the Adaptix software, we were able to send commands to do the different stages of the robot arm, while at the same time collecting sensor data from all of the entire system. So we were able to optimize the speed of different kind of essentially gestures that the machine was doing, and to speed up the overall process that way and know that we weren't doing anything that was detrimental to the throughput or the actual yield. And then finally, once the manufacturing process is finalized, what we want to be able to do is identify any deviations or anomalies in that behavior from what's what we're observing. So we want to kind of solidify that and then notify the tool owners if there's anything going wrong. So this final solution was successfully deployed on over 100 machines in the factory, and they saw an increase in throughput by over 50% through the process of the entire project. So it was really great success for us building out this solution. So here's an image of one of the machines that we worked on. And so what you can see here, so what you can see here is there's a lot of different parts. There's an LED cure, there's a goniometer, which is used for really high precision movement and alignment of the part. There's conveyor belts. So there's a lot of really rich sensor data that we're able to pull off this machine. And we also have our over-the-top sensors attached in different places, and we're running all of the edge computing locally at this machine. And then really what we want to deliver to this customer is not like TinyML models or machine learning. What they're really interested in is this high-level dashboard view. So it's really critical for us to work with these other partners to be able to deliver that. And so here's kind of one of the screenshots of the dash-level view. And so the customers are able to look at the history for all of the sensor data that they're reading. When we're running models, we're recording any anomalies that they see, so they get a kind of overall summary health of each of the components. They can go in and see instructions for maintenance for different things. So they're really able to grow with this platform and kind of make it their own. And so it's not just doing the anomaly detection and the predictive maintenance, but it's bringing a lot of high-level aggregate information right to the technician. So I think that's one of the reasons why it's so successful. So where does TinyML fit into this solution? Let me just give a kind of a little bit higher level view. So in this image, yeah, right here. So right here, this is kind of an overview of the solution that's deployed. So you have the EdgeOps software running each of these down here is an individual machine at the factory floor. So inside a factory, they may have 50 or 80 different machines running. The EdgeOps software is running right there. They also have a site view, so the data is on a network and it's being pushed up to a site view, and then all the way up to an enterprise view where they have this deployed across multiple sites. And so the EdgeOps autonomous system platform is orchestrating that data flow. It's deciding when to run the analytics and the machine learning models. It's automating the tool workflow, so it's telling it, sending the commands to do the different processes within the machine, and aggregating all that data into the dashboard view. And then using our SensiML toolkit, we were building TinyML models that would run for real-time time series classification and anomaly detection all the way down at these edge machines. And so, like I've been saying, TinyML was only part of this solution, but it did add a lot of value. One of the key things was making it easier to deploy models as close as they needed to the sensor. So they didn't necessarily have to worry about switching frameworks if they wanted to run really close to the sensor on a microcontroller or a Raspberry Pi, or even higher on like a gateway type computer. Another thing with the TinyML is you don't have to worry about deploying a Docker environment. You don't have to worry about deploying what package of Python libraries in any of your DSP. So within our framework, once you build the entire model from raw sensor data it includes the DSP, it includes the feature extraction and the classifier, all of that gets compiled into a single C library that you can link against. So the API is very simple. It's a run model. You pass in sensor data, and you pass a model index. And because, and I guess one more thing to say about that is that our software allows them to run multiple models at the same time on commodity hardware. So each of these machines, we're running 60 to 80 different models in real time. And so with our library, when you go through and you build multiple models for each different step of the machine, you can then compile all of those models into a single library, which makes it really, really easy for them to deploy on the infrastructure. Okay, so here's actually an image of one of the data that came off one of the robot arms. And so these different regions in red, yellow, and green are different stages that the robot arm moves through. And so one of the key aspects for us to be successful in doing predictive maintenance on this is we need to know what the robot is doing at each step of the way if we're going to be able to build an anomaly prediction model. We don't want to have to identify, what is the robot doing and then try and guess if what it's doing is anomalous or not. So because with the Adaptix software, we're part of the control workflow, What it does is it says, OK, here, tell this robot arm to move from here to here. It's aggregating all the sensor data while that gesture is occurring, and then we can run a model against that sensor data right there. And so in this process, we're actually, this robot arm movement is segmented into about 9 different steps. And at each step along the way, we're going to label that data, create a training data set for it, extract feature vectors, and run some anomaly detection algorithms on it. And that becomes our TinyML application runtime library. And that's all included into the EdgeOps platform. So it's responsible for aggregating that sensor data, doing the time synchronization, running the machine learning models, and then putting that all into an event log that's useful to the end users. So I'll step back just a little bit and give you an overview of the SensiML products. So we have the Data Capture Lab, which is for time series data annotation. So it works really well with audio or any time series sensor data. This example that I'm showing right here is accelerometer and gyroscope. So you can see visually the accelerometer and gyroscope. You can sync it up with video down at the bottom, so you can move it along and you can label individual parts. You can ingest data through a CSV or WAV file, or you can also capture data using a simple protocol over Wi-Fi or TCP/IP, BLE, and serial port. And then you can also get a really high-level view of your project. So you can see capture data for multiple times. You can add different metadata to each of those individual captures. It's a really performant desktop software. It's easy to load 100,000 files. It's easy to open files that are maybe an hour long with thousands of labels on them. So it's a great tool for labeling and exploring time series sensor data. We also have the SensiML Analytics Studio, which is for building machine learning models. So this goes through querying data, labeling data, model visualization, and AutoML model generation. You can test your models, and then you can download models that are optimized for edge device. And then for this project specifically, we used our Python SDK quite a bit. The Python SDK lets you programmatically define what the model should look like. So for this robot arm, since we're building a model for each of these individual steps of the robot, we would use the Python SDK to build the model. And then once we're ready to deploy it, there's a simple API where you basically can specify the model UUID. You can give it a name. You can tell what sensor data should go into it. And then you can compile it all into a single library. And that gives you a really easy API to call. And so just to give an example of or a couple of examples of some of the stuff we saw as we were building out kind of the time series classification. So this is what the sensor data coming off one of the mnemonic actuator looks like. And when we're building the models, we're just assuming, when we get started up and running, we have to assume that the machine's working correctly. So the technicians, we're working with them, and they say, yes, it's working. So as we're building the model, we're collecting, and we're saying, OK, this is our original data. We assume it's good. And we use this to build our initial model. And then as the machine started running, we started seeing anomalies being detected for that model we had built. And then we went and looked at the data. You can see actually at the end, there's a little spike that's showing up. And this was indicative of a problem actually with that mnemonic actuator. So they went and replaced that part. And then when we started collecting data again for it, the spike has completely gone away. And the signal is actually much cleaner. So this was really a great example of how you can deploy these models. And they do work really well for detecting the anomalies. It's just really critical that you're able to know the context of the machine. So for us, working with the Adaptix software, we're able to know, what the machine is doing, what the context of it is, and always running a model against that specific data set. And so here's another example with a linear motor stage. Underneath, you can't really see it too well, but the blue data was the original good data that the model was trained against. And then over time, you started to see some excess vibrations, which are in the red data. And that was, again, another indication of a failure in the red part. So initially, we would build models to detect anomalies. And then as we started to understand the machine better, we could build predictive models to look for these specific features. So thanks, everyone, for listening. So again, our partners with the EdgeOps platform is our Adaptix. You can reach them at sales@adaptix.com. And then you can reach us at SensiML, so support@sensiml.com, or you can reach out to me directly, KNOROWSKI@sensiml.com.
Thank you, Chris. I'll start with a quick question. If there are any questions, please come up. So really interesting use case. You talked about like how you found an anomaly in the data set that you used to train the model, right? I'm curious, what was the process to?
Yeah, so are you talking about this,
yeah,
in this case here? So we didn't find an anomaly in the data set. The blue was the initial data that we collected. So we trained the model to say, this is what the normal data looks like, because we hadn't seen anything wrong yet. And then when it's actually running in production, we started seeing the model was flagging anomalies. And then when we looked at it, we could notice that this peak was showing up at the end of the data set. So that went and worked with the domain experts on the tool, and they just went and replaced the part. And they saw this nice clean line afterwards. So.
Okay, fine. So perfect. Thank you for clarifying. Yep.
Hi, great talk. So I have a couple of questions. So the first one is, what is sort of the key benefit for doing this on the edge as opposed to just ingesting things into like a backend and then doing the analysis there? Mm-hmm. I didn't get that part.
Mm-hmm. Yeah, so doing things at the edge, you don't have to send nearly as much data up to the cloud software. So with Adaptive software, they have all of the analytics running locally at the edge. Everything's right there. The dashboard's right there where the technician can look at it. So I think there's huge benefits there. The compute's much cheaper. It's much easier to figure out when things are going wrong. So with EdgeOps software, you have the flexibility to kind of see where do you want your data to live eventually. But definitely, there's huge advantages to doing that down at the edge.
I see. The other question is, you mentioned over-the-top sensor placements, and of course, in a real factory environment, things are going to be very, very unique. Unique is going to be the name of the game. So is this kind of all done in a few-shot way? Or is it like a human-in-the-loop thing where the technician is kind of giving you the all clear or not? Like, how does this scale? That's what I'm trying to understand.
Yeah, so with these in particular, I think really a lot of the scalability comes from the platform being able to segment that data. So, as you give a machine control, you are collecting all of the sensor data for that specific gesture and collecting that to a single place. And that's really where I think a lot of the scalability comes from, because you're not doing this huge intractable problem anymore. You're focusing on a very specific gesture. And so that lets you do things like do the anomaly detection when you see these deviations. When the manufacturing processes are very consistent, it becomes pretty obvious when something's going wrong if you're looking at it in the right way. So I think a lot of the scaling has to do with that. So they have teams of data scientists that work on deploying the models, training the models, redeploying the models, but they've had a lot of success with it. So I think that's really key, though, is being in that control process and being able to segment the data in a really smart way.
Hey, Chris. You mentioned that you were deploying something like 50 to 100 models in these firmwares. Why do you need so many models?
Yeah, so in this case, there's a lot of different gestures that these robots are going through. So you have the conveyor belt, you have this goniometer, you have the LED cure, and each of them is a completely different step in the process. And so you want to monitor each step that of the manufacturing process for issues that could come up. So each kind of stage in the process is a different model.
Okay, I see. Thanks.
Okay, thank you, Chris. Thank you very much.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving TinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SensiML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Siva, EMSA, Greenwave Technologies, Gravity, Hymix, HOTG, ImagiMob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.